looking at geometric probability. This is a ratio that involves geometric measures. Often we're going to use like length or area, any type of like measurable category or stat. We can create a geometric probability. So let's look at kind of like the first example here. What is the probability that K is on line segment CD? So they're basically saying if we randomly put point K anywhere here, anywhere on this line, what's the probability that it would land in this area? So to figure that out, we would take the length of CD. So again, whatever that is, we may have to do some math to figure that out. And then we're going to put it all over the whole thing. So what's the whole sample space that you could compare it to? You could compare it to AB. So find the probability that a point K randomly selected from AE will lie on the given segment. So let's first look at AE. So AE goes from negative 12 to 3. Negative 12 to positive 12. So the distance of AE is a total of 24. And the first section or the first part of the question is asking me for D to E. So D to E goes from 3 to 12. So again, if we wanted to format it like this, the probability that K is on DE is equal to 9 over 24. But we always want to reduce if we can. So 3, 6, 9, 12, 15, 18, 21, 24. They both have a 3 in common. So let's divide the top and the bottom by 3 and get 3/8. BC. Let's find B and C. B to C goes from negative 3 to negative 6. Distances are always positive again, and we're moving from a smaller number to a larger number. So BC, the segment is 3. Same idea. I'm going to divide by 3. This time I'm going to get 1/8. 1/8. What is the probability that K is in the region M? Again, this time I'm looking at area, but the idea is the same. If I randomly picked a point from this area, what's the probability that it would land in that red region, that region M? Well, again, there's no numbers on here, but what we would do is we would look at the whole area of that red region M and then divide it by the whole area of the region J. Again, what we've come back to and what we've looked at a lot is this part to whole relationship. How do I look at part of it and compare it to the whole thing? Find the probability that a randomly selected point will lie in the shaded region. All right, so I see that I've got a triangle, and the area formula for the triangle is 1/2 base times height. Base is 6 and height is 14. So 1/2 6 times 14, 3 times 14 is going to give me 42. So the area of this is 42. Now we got to find the area of our big triangle, the whole thing. So this time I'm going to use different color. My area is going to be 1/2. Base is 12, height is 14. I made a mistake on the previous one because the height of my small triangle is not 14. The whole thing is 14. This is only half of it, and because of this congruence marker, that means this is 7 and this is 7. So I have to change this from above. 6 times 7 divided by 2. Again, my answer is just going to be cut in half. But my big triangle, my whole triangle, I do have a height of 14. So maybe just clear that up. So 6 times 14 is 84. So if we were to come up, what's the probability? The probability that it would lie in the shaded region would be 21 out of 84. My guess is that we can find something that these can be divided by. And actually, we could divide the top and the bottom by 21 and get 1/4. So there's a possibility, 1 out of 4 chance, that a randomly selected point will be in that shaded region. Similar type of problem. Again, here's my shaded area, this time dealing with circles. So let's use our abstract brains and think critically and say, all right, the radius is 6, which means the radius is going to be 6 here, the radius is going to be 6 here, and the radius, in this case, this is the diameter, is going to be 6. So the area formula is pi times radius squared. I'm going to take my little circle and compare it to the big circle. Boop. And so my little circle, if the diameter is 6, that means the radius is 3. So I'm going to say pi times 3 squared over, and then my big circle, the radius is actually 6. So pi times 6 squared. So again, 9 pi over 36 pi. I can simplify this. Pi divided by pi cancels out. And dividing both sides by 9, I get 1/4. So same actual probability as the problem above, but one was with a triangle and one was with a circle.